But yeah, I'm gonna go through the high-level overview of stir and try to explain the best I could. So yeah, bear with me. Okay, so let's first talk about what stir attempts to do, or how it improves, so to say, theoretically over fried. So in fried, what we are trying to do is we are trying to basically say, given a given a Reed-Solomon code word, I want to find essentially, I want to test the proximity between, or the proximity in which, I want to test the proximity of the polynomial so that I know it's with high probability it's the correct one, right? That's how roughly it is. So what stir wants to do is given a, so what stir essentially wants to do is, what it essentially does is it reduces the domain. So here f is finite field, this is the domain of the polynomial, and d is the degree of the polynomial. So what stir wants to do, or what stir does, is it makes phi queryless by essentially increasing the rate, the code rate, which basically creates more redundancy in the Reed-Solomon code, and that helps it check for distance easier, or it helps it essentially find that easier because of the redundancy. So in stir, it tries to essentially get something called, the C prime, tries to find this by, given this, tries to find something called L prime and the, so, and this domain, it actually is, so yeah, it reduces the domain in which you have to query by 2, where Fry originally reduced the domain size by n divided by k, where k is the folding factor in this case. So yeah, that's essentially what stir improves on, so to say, from my understanding. Okay, so I'll also go through the protocol a little bit, and yeah, so I'm going to go through a little bit of how Fry works. So how Fry works, essentially, it's every round it folds, and I think it's explained every round it folds, and this basically eventually reduces it to a constant polynomial, which is easier to evaluate and then check against. And each step, it's actually committed, Merkle commitment. In this case, again, because it's a improvement of Fry, it's also have this round by round mechanism in its protocol. And so yeah, I will go through in each iteration what happens. So I'm just going to do this. I'm going to write it down first. So R4. This is G over. Okay, I'll explain it a bit first. So the first step is the same as Fry, in which the verifier will send over essentially a random value for it to perform for the folding step, and this is similar to Fry. And on the second step, it starts to differ. So on the second step, it will basically take G, a polynomial, which is a folded polynomial over, which is a folded polynomial, G hat here. it's the result of folding the initial function f, and this g hat we then evaluate it over the half domain, and that basically gives us the result of g, which is essentially the evaluation of g hat over L prime. Yeah. And this is sent over, so the prover computes this, and this is sent over to the verifier. And now we actually sample out of the domain a value we call R out. It's also from the field, but it's from the field that is not currently in the evaluation domain. This is again sampled by the verifier and sent over to the prover, so that the prover can essentially give the result of evaluating this with g hat and producing an output we call beta. Oh, sorry. Yeah, this evaluation result is sent over to the verifier by the prover. This is computed by the prover and sent to the verifier. And so, from my understanding, this two-step comes from the deep paper. If I'm not wrong, it's supposed to improve the soundness, but I'm not very sure about the details on this. So, finally, not finally actually. So the fifth step, the verifier will sample what we call shift queries, which is essentially random values. Sorry. Yep, this is random values generated from or sampled from, I believe, the domain of, I think this one I'm not sure. Okay, so yeah, so this one, right? Okay, so RI shift is sampled from this, and this is a little bit different from this, which is n divided by 2. It's the domain evaluation of the full factor. This actually equals to n divided by k, I believe. Yes. So this is sampled, and the prover computes yi, which actually it's similar to this, but it's the folded. Oh, it's okay. This is a bit confusing. So it's a folded function of f in regards with f fold. This is similar to this in the sense that g hat is an extension of folding the origin function, where this is just the result of folding the origin function with R fold. And by computing this, you get you compute this over the shift query, and then on the next step, you actually use the result of this computation to compute a new polynomial, which is then used in the next iteration. The new polynomial is computed via taking the quotient of g, which is your evaluation of the folded polynomial extension, over, so you take g and you calculate the quotient with the result of, let me check, give me a moment. with the result of beta, and also the result of computing it against these RI shift queries. Yeah, this is roughly what an iteration looks like. Yeah, I'm still looking at the code to understand a little bit with more clarity. Yeah, that's essentially it. So, any questions?
So the stir is just optimize for the process?
It's mainly to reduce, so this is the evaluation domain, I believe, yes. So it's mainly by reducing this, it improves, so it reduces the amount of query you need to do in each round. So because in Fry, each round you have to do a certain amount of queries and then keep doing it until the last round. It still reduces the amount of query, no, the amount of query doesn't reduce, sorry. You have to do a certain amount of query so that it's sound. So in this case, by reducing the evaluation domain, it reduces the amount of query you need to do to make it sound, and thus that reduces the, it basically improves the efficiency of doing the commitment. Yeah, by reducing the amount of queries you have to do, it reduces the complexity, and yeah, you get this.
Who's next? Who want? Okay.